Measurement is perhaps the most well-known, yet misunderstood concept in quantum mechanics. In this video, we will explore what measurement is on a quantum level, how we can represent it mathematically, and how this leads to a deeper intuition about the nature of reality. In the second half of the video, we will discuss what it truly means to measure something, and how we can derive the most general type of measurement in quantum mechanics, the POVM. Consider a cat, placed into a box along with a device, where some quantum phenomenon has a 50% chance of happening. If it happens, the device releases a poison, killing the cat. If it doesn't happen, the cat remains alive. In quantum mechanics, the state of a quantum system is defined by a state vector or wave function. Any physically possible state of the system, in this case either alive or dead, is called a pure state. If we know the pure state, we have all the physical information about the system. We'll write each vector in Dirac notation, as it will help us see what's going on later. The right-angled bracket or ket vector is just a normal column vector, and the left-angled bracket or bra is the transpose conjugate, so a row vector where each entry is the complex conjugate of its corresponding ket. The set of all pure state vectors forms a complete orthonormal set. Orthonormal means that the scalar product between any two state vectors is 0, unless the two vectors are the same, in which case it's 1. The set being complete means that we can write the wave function of any given system as a sum of all the possible pure state vectors of that system with some weighting Cn, which is in general a complex number. This is called a superposition. In some sense, the system is in all of these physical states at the same time. For our cat, there are only two possible pure states, alive or dead, so we can write the cat wave function as a superposition like this. It's important to realize this is different from saying we do not know whether the cat is alive or dead. A superposition means there'll be interference effects between the cat alive and cat dead states, much like two waves can interfere with each other. For a system as large as a cat, we cannot observe these effects, although they are still there. This is called quantum decoherence. The more variables a system interacts with, the less obvious quantum effects become. This is why we do not observe quantum mechanical effects in our everyday lives. If you were to perform a similar experiment with something like a photon, as in the famous double slit experiment, the quantum effects would become obvious. Returning to the example of our cat, the cat's in a superposition of both being alive and dead. Yet when we open the box, we do not see a mess of cat alive and cat dead. We see one outcome or the other. By opening the box, we measure what's inside and are left with a final state. We say the act of measurement collapses the wave function into either alive or dead, with probability equal to the coefficient squared. The act of measurement on this simple system can be described by first considering the Hermitian operator O, written like this for our cat, or more generally as a sum, where the vectors, the Dirac notation kets, are the eigenvectors of the operator. This operator represents an observable quantity, and the operator being Hermitian simply means that the eigenvalues, this an, are real and correspond to the thing being measured. For example, this could be the energy of an associated state, or the aliveness of a cat. If we perform a measurement and measure the particular outcome am, the wave function collapses, and we know that the system is now in the pure state am vector. The probability of measuring this outcome am is given like this, which is just the coefficient squared as before. The eigenvectors of the observable O form a complete set in the system space, so we can write the wave function of a system over the sum an vector, which makes our calculations a lot easier. This type of measurement is called a projective measurement, as the state of the system post-measurement is an eigenstate of the measurement operator O. I think Dirac notation makes it more intuitive what a projective measurement means here. We can see that for a particular measurement operator, O is this outer product of an vector, then all the inner product terms are orthogonal and go to 0, apart from the an vector term in the wave function. So in this sense, we are projecting onto this vector direction. Let's now take a small step back to recap and think about what's going on. We have a quantum system, which we can describe using a superposition of all possible physical states. We have an observable with outcomes an, corresponding to associated final states of the system an vector. When we measure the system, the final state is determined probabilistically, with probabilities we can calculate. And the value we measure is an eigenvalue of the observable, and the final system state is that associated eigenvector. This last point may seem simple. If we measure the cat is alive, the state of the cat is alive. However, Imagine we are trying to count the number of photons emitted by an atom in a box. We do this by waiting a small amount of time, and then making a small opening where we place a detector. All of the photons bounce around and enter the detector, and we count how many there are. Here, the system in question is the box, containing an unknown number of photons, and we assume we can accurately count all the photons, such that the final state of the system contains no photons. We remember that the post-measurement state of the system should be an eigenstate of the observable, with eigenvalue equal to the real quantity we've just measured, in this case, the number of photons n. This is clearly not true here. To measure the n photons in the box, we have absorbed them, removing them from the box and leaving the box empty. The eigenstate of the box, 0 photon vector, and the measured eigenvalue, n photons, do not correspond to each other. What we have established previously implies that if we've measured n photons, the final state of the system should also contain n photons. But we've found an example here where that is not true. How can this be so? What this example is showing is that when we measure a system, we aren't really measuring the system itself. Rather, we are measuring the effect that system has on its environment. To describe this process, it's insufficient to use projective measurements. Of course, there really is a chain of interactions between the atom and the electromagnetic field and the detector on the computer in your eye, and so on and so on. We can describe the interactions between the various systems, but at some point along the chain, we must make a cut by applying a regular projective measurement. This is called Heisenberg's cut. In this example of photon counting and most other quantum optical systems, we simply apply a projective measurement to the electromagnetic field around the atom, rather than the atom itself. To describe this more general type of measurement, we use something called a positive operator valued measure, or POVM. If we have a system and a measurement apparatus, labeled psi and theta here respectively, the initial state of the total system being the system and apparatus, is given by the state vector capital Psi. The use of the tensor product here simply ensures we have enough dimensions in our state space to allow for all permutations of the subsystems. We won't explicitly write the tensor product every time. We simply use this condensed form of Dirac notation. As I'm working through the maths in the background here, which you don't need to pay super close attention to, I'm simply deriving the form of the measurement operator by finding the final state of the system after they've evolved together and we measure them. We find that the measurement operator takes a fairly simple form, which you will see in a minute after I finish my calculations. The measurement operator is defined for a particular outcome m. You may remember it being the outer product of vectors as before. It is simply the measurement outcome eigenvector on the left. In the middle, we have this unitary operator u of big T1, which simply describes how the systems evolve together over this time, big T1, before we measure them. And on the right, you have the wave function of the measurement apparatus. We can also easily calculate the probability of measuring the outcome, where we define this inner term as something called an effect. It's just a new operator. The set of all effects and probabilities constitutes a POVM on the space of all possible measurement outcomes. The post-measurement state of the system can be easily calculated from this result here, where M and P are the measurement operator and probability as defined on the previous slide. Let us return to the example of counting the number of photons in a box to see if we can get the correct final state of the system now. We begin by defining the set of all measurement operators like this, which is simply the outer product of the vacuum state and the number of photons we have counted. Note here that the number of photons counted, this AM vector, forms a complete set, so we can write the wave function of the system in terms of this eigenvector. We can hence define the effects from the measurement operators, and use the effects to calculate the probability of measuring any given outcome. Now, to calculate the final state of the system, I'm going to do it in terms of the density matrix because it makes the calculations a lot easier. We work through the maths, and we can see that we get the correct final state. The system is in a vacuum. This type of measurement and calculation could not have been performed without the concept of a POVM. In this video, we have shown how measurement works in quantum mechanics. We've introduced the ideas of superposition and projective measurement, and we have shown how, in order to describe measurement on real systems, we must carefully consider the system, the environment, the measurement apparatus, and the interactions between them. This work forms a small part of a research project I undertook over the summer, investigating bounds on continuous jump measurements in open quantum systems. If we choose to count the photons emitted from the box not at discrete intervals but continuously, then what is the most information we can learn about the atom emitting those photons? The answer turns out to be a little bit long, at least at finite times, but I include this explanation at the end of the video to give you a concrete example of how these techniques we've covered today might be used to perform cutting-edge physics research. Thank you for watching.